I'm here today to talk about the soybean part of this. And I went around and around and around. Lee will attest to this, that I spent a long time trying to get my slides put together for this because I didn't know exactly how to pursue this because there's so many angles that connect soybeans and corn. So I'm going to talk just a little bit about the corn. There's a little quote in the program that says soybeans are important to a successful Minnesota pork industry. And certainly, from my standpoint as a soybean person, the pork to the soybean industry. So it's very much entwined. I don't want to get too overly verbose or anything about this, but it's really that these two share an entwined destiny. Soybean, a lot of folks from the city, just like corn, they think that, you know, corn on the cob is what all farmers produce, and they think that soybeans primarily go for tofu. But certainly swine is the biggest customer for our soybeans. It's a very important part of our industry, and that's the piece I'm going to give a little bit today. So my job description at the university, I'm in extension. I'm out educating producers about growing soybeans in a more profitable and environmentally sustainable way. And I do a lot of applied research and some basic research on campus as well. My goal is really to help farmers produce the greatest yields with the fewest inputs in the most sustainably sound way, and all the time producing a crop that has value in the marketplace. And what I'm going to talk about here is mostly on that latter part this morning, is about the value piece. I do a tremendous amount of work trying to increase overall production, increase yields. That is key that's a key piece for the hog industry, because we need a plentiful supply of soybean that's local, that doesn't have to be imported, low basis, so that we can profitably feed soybean. I'm going to talk a little bit beyond that and talk about the quality bit that we've been spending a lot of time working on at the university, and try to put that together with how it helps the hog farmers. So how does all this affect the producer? Well, obviously, most hog producers in the state are also raising soybeans. But certainly there's a connection, even if they're not directly doing that. They're within these communities. But indirect is the most important part here. My job is to help supply the greatest quantity of high quality soybeans to the market. So more, better, and even cheaper, I think, is an important piece of this. Although it's hard to talk to the soybean producers about cheaper, but that's really what happens as we produce more and more, as we put more in the marketplace, and allows the local price to be lower. So I'm going to talk just maybe 10 more minutes here this morning, and incidentally, I am going to have to book out. I do have another commitment at 11:30, and so I'm going to have to slide out to the back of the room. 12:30. I will, these are the things that I'm going to talk about here this morning. Talk about a U.S. soybean quality survey that we conduct for the national checkoff. We're also doing some meal studies looking at meal quality. And I'm moving more and more into the analytical side in looking at quality in soybeans, so we're doing some meal studies now. Also doing studies of soybean physiology and how the plant and the environment interact to produce great yields as well as high quality soybeans. And then just briefly about a project that I'm really interested in. I'm just going to highlight a little bit of some of the data from a mutagenesis project, and then what I'm supposed to do is spend some time talking about the long-term view, and I'm just going to give one slide on that at the end. So we conduct a survey of the U.S. soybean crop, where each year we go out and ask producers to send samples of their soybeans to us. This is primarily an international marketing effort to provide the international buyers with some depiction of where the best quality soybeans are in the U.S. and how the U.S. crop relates to previous years. This is just a county-by-county map that shows where the highest quality soybeans are in terms of protein concentration. You can see that we tend to be a little bit, these lighter colors are the lower protein areas. The darker regions are higher protein. Typically, year after year, the highest protein soybeans are in the south. That over years, that tends to decline as we go north and to the west. Typically, our lowest protein soybeans are in the far north and west, and the highest in the mid-south. So this year wasn't atypical, but there was a few little areas that were a little bit different than what we normally see. And this is the kind of information we take overseas. And certainly the domestic crushers are using this data in addition to their own data that they're collecting. The domestic crushers are going out and finding, they actually have the first chance to get most of these soybeans. So they're identifying the highest protein soybeans in the fall and sourcing those wherever they can to produce the highest quality meal for the domestic market first. Most of our exports are actually taking what's left over. So I just want to assure you that we're not selling off the good beans first in our overseas efforts. This just shows a little bit different type of way of looking at the data. This data, we use GIS to basically to plot all of these individual samples back to the farmer where they came from. So we had 1,800 samples this year, 1,810 or 20, something like that. And these points represent where those came from. There's zip codes, so there's multiple samples will come from any individual point, but it does highlight with quite a bit of specificity where different soybeans of different protein and oil concentration come from. I'm just showing the protein figures. We also do seed size and foreign material and a lot of other things for the overseas customers, but this just gives a little bit more detail. It's a little bit of a sideline, but there's more and more interest in exporting by containers, so I'm always asked by the international guys what are the soybeans around Chicago or around Omaha, around Fargo, what are the different quality levels for those. Of course, that's a very small volume that goes that way, but interest to those folks. I'm also have done, and I've finished this now, but I had 6 years of data from Minnesota itself, and this is the last year in 2008. In that year, we received 645 samples just from Minnesota. The basis of this is trying to understand what environmental cues drive or environmental effects drive protein and oil concentration in soybean. The idea here is to better identify regions that have a better utility for producing high soybeans for domestic crush or for edible soybeans, or high oil regions. At the time when we were looking at this, we thought that biodiesel was the answer, so we were really interested in high oil concentration areas. Shown on the left here is the protein map. Because we grow different soybeans in different regions, we are able to index all these to a common variety, so they're indexed. If we could grow this one particular soybean throughout the state, this is the map of this particular year where how the quality would vary. In that particular year, we had higher protein in the west. There's almost universally each year a low protein right in the central part of southern Minnesota, and then we typically have high protein off to the east. And typically we decrease protein rapidly as we go to the north and west, but this year we had good protein all the way. Protein and oil are tightly inversely related in soybean, so where we had high protein regions, over here we tend to have low oil regions shown here. So one of the things that we did learn from some of these studies is the tight correlation with not protein but oil to the temperatures that are found during seed filling. And we determined that and this is fairly rough, but just the approximate period of seed filling between the 15th of August and the 15th of September, if you look at the temperatures, the average temperatures within a region during that period, that very well predicts the oil concentration of the seed that's going to be harvested from that area. For this, the utility here is that a buyer can go out and look at current environmental data and determine what areas are going to have higher and lower oil if they're interested in sourcing for that. And you can see that it's not huge, but we get about 1/3 of a percentage point for every degree Fahrenheit increase that we have. So every 3 degrees Fahrenheit increase on average that we have during this period, which is not, obviously we have regions and years when we had a very broad range. This is Celsius here, but we have, this is often, we have enough variability year to year and across regions that we can very easily capture. And this explains most of the difference in oil on a yearly basis. So a little bit about meal. There's a concern because, again, we tend to grow low protein soybeans in the north. Minnesota and the Dakotas have the lowest protein. There's been concern about the meal produced from those. In fact, there's been a lot of people that have been promoting northern soybeans as perhaps having higher quality in terms of their amino acid balance. Our data shows that we're at least equal to, if not potentially just a little bit tiny, and Lee will probably say unimportantly not significantly greater. But the northern soybeans tend to, even though they have lower protein on average in the meal, certainly cysteine, methionine, lysine, tryptophan are at least equal on a percent of the protein basis. So those amino acids are at least as abundant in the protein fraction as they are in the south, and probably a little bit better. This is just this year's data set where we looked at around 60 samples from crushers throughout the U.S. And all we did here was plot these in order of percentage protein in that meal, from 45 to around 48% or so in order. First of all, you can see that the meal coming out of these plants is broad. There's a wide range in protein. We also included lysine concentration as well. And shown here, the lysine concentration doesn't vary as much as protein concentration, although there's a tremendous amount of scatter. It shows that sample-to-sample variation in lysine is huge, like most of the other amino acids. However, the slope of this is smaller. It indicates that at low proteins, those samples tend to be slightly enriched in lysine relative to the very high protein. Basically, when we're producing this, the protein is being deposited in the seed in the plant, in the field, at very high levels of protein. Those essential amino acids tend to be a little bit diluted out with non-essential amino acids. And just a couple more slides. I'd like to talk a little bit about some of my future, the direct future that I'm involved with, and I'm involved with a project where we've taken a Minnesota variety, a conventional variety that we could use for breeding purposes. It tended to be a high protein variety anyway. We put it through a mutagenesis process with fast neutron mutagenesis, and this allows us to quickly get more genetic variation within this population. So the group that I'm working with started at about 7,000 lines, and we keep slicing that down and looking at quality parameters among these and looking for unique phenotypes or variants within that. Some of the most advanced material here I grew in St. Paul this year. I had 3 families. I had 2 that showed very high protein. So the mean of these families was around 36% protein, But these two particular families, these are groups of 10 lines each, had 40 to 41% protein. On the other hand, I had a set of lines with 29% protein. So this one ended up with quite high oil relative to the mean. This isn't tremendous oil, but relative to this, it was a very high oil line. So we have some lines that are high protein, some lines that are high oil, and these are just examples of some of the things that we found. These we can move forward and move into a breeding program after we understand a little bit better about what is causing these differences. From a really academic and physiological standpoint, I'm really interested in these lines because clearly there's something happening with protein deposition in this variety or in this line. The protein is backed up for some reason. It's not being laid down properly because oil is high, but there's also sucrose, which is likely a precursor of a lot of sucrose is coming into the seed as the energy source for putting on protein and oil. High levels of sucrose in the seed relatively high relative to the mean. It indicates that it's backing up, and so there's a problem on this end. If we understand what those problems are, we're better able to get around those. We may actually make more progress increasing protein by understanding how this one functions even than perhaps this one. So we're looking at the whole pathways to better understand these so we can produce soybeans that have a higher intrinsic value and eventually can produce meal that has a higher value to the end user. So one last slide, I want to talk just briefly about the future in terms of soybean breeding effort. And I know Lee wanted some firm answers on this, and I wasn't able to provide those. But certainly the breeders are looking at a better amino acid balance in the soybean protein so that we don't have to add synthetics to the feed. This is complicated because soybean itself we call it an oil seed, but it's really a protein producing plant. And the soybean has a lot of redundancies in how it produces protein and how it lays down these storage proteins. And so making alterations to the protein part of this is quite difficult. The oil is actually a little bit easier. And I'll say right now that the industry is really moving towards looking at high-value soybean from a breeding standpoint more for the oil value, for industrial uses, and for human consumption than they are for meal and looking probably at your industry and specifically. I do think, though, that there's going to be feedback, especially from the human side, as we know more about some of the quality factors that affect human health. There's obviously there'll be quicker translation to swine than a lot of the other livestock sectors. We're also looking at reducing trypsin inhibitor, low phytate. These are all in the process now, but certainly everybody's moving towards lower and better. Low raffinose, stachyose. Again, these are some of these soluble sugars, and then higher protein overall will be a benefit.
Our next presenter is Dr. Lee Johnston, who's a swine nutritionist with the swine group at the University of Minnesota. He'll put some of this survey information into motion as he describes how pork producers can capture these traits in their swine nutrition programs. Welcome, Lee.
Well, thanks, John. As John mentioned, my mission or assignment in this was to try to build off of what Seth has presented to you and see where pork producers can capture some of that value. Given the short time we have and as many things as Seth laid out, I picked out basically two that we have some recent data on and some others to share with you today. So basically soybean meal, it's coming into animal diets as the primary amino acid source. Seth mentioned it's dependable supply, generally inexpensive in terms of price. Unfortunately, it does have some anti-nutritional factors that come with it that we have to deal with. And we think about it as an amino acid source. The thing I want to get across to you a little bit about is how the pig makes protein. And this is kind of a schematic drawing. If we look at this string here as a protein chain, and basically we feed soybean meal to supply amino acids because they're the building blocks of protein. I don't, as a nutritionist, really care how high the protein is. I want to know what the constituent amino acids in that protein are. And we're trying to get this protein chain, and you can call it a muscle protein or a milk protein or whatever you want. And in the cell, there's an RNA code. Just going back to your high school biology now, if you can dig that far back. And this code basically is taken from the DNA in the cell, and it's basically the recipe. It says what amino acids do we need to link together in what particular order to make this, let's just say it's a muscle protein. And so what this code does is on the ribosome, it says, it's looking right here, and it says, well, the recipe says we need a lysine. So it goes out into the cell, and it finds a lysine, and it brings that in, and attaches it, and it ratchets one amino acid onto the chain. And then the next ingredient in the recipe might be, say, a leucine. So it'll come over here and it'll grab a leucine, and it'll add it to the chain, and so on and so forth. Everything works good if there's enough of these essential amino acids floating around in the cell. But if for some reason we come up and the recipe's calling for tryptophan and there's none to be had, it doesn't just say, well, isoleucine's pretty close, we'll put that in. Pretty much it just stops. Protein synthesis stops until there's more supply, or in long-term cases, maybe they'll start to break down that protein. And so it's important to have the supply of all the essential amino acids there in the cell when protein synthesis is taking place. And I say essential amino acids, there's basically 10 that the body cannot make in high enough levels to satisfy the needs. So they have to come in through the diet. And so basically this is the concept. You can think of this kind of all or none thing. Either you got all the ingredients to make the protein or you don't. And our job as nutritionists is to make sure that all those amino acid ingredients are there at the right time to make the proteins that the pig needs. So if we look at that, if we went into the National Research Council's requirements for a growing barrow, I think I picked about a 150-pound barrow or something like that, and we list all the 10 essential amino acids across the bottom here, and NRC gives us a % in the diet. And so basically, if we look over here at lysine, it says we need to have somewhere around 0.78, 0.77% of the diet. This is on a total basis. And we see that leucine is somewhere around there, 0.75 or something like that, and so on. Some are needed in smaller amounts, methionine, tryptophan, and some of these others at intermediate levels. So basically that's our target in the diet that we got to meet. Well, how will we do that? Well, what do we feed pigs? We feed them corn, right? It'd be a lot easier, no disparagement to the soybean growers, but it'd be a lot easier if we just feed them corn. We have one ingredient, we put it in there and call it good. Well, if we were to do that, and years ago they did do that, we would see that the lighter bars here is the pig's requirement. The dark bars is the amount of amino acids that would come into the diet if we just fed corn. And we can look at arginine and see that bar is higher than the requirement, so we're covered on that one. Histidine, that's pretty close. Isoleucine. Corn doesn't supply enough isoleucine to meet the pig's requirement. Got tons of leucine. Lysine. Look at the huge disparity between the requirement and what corn is going to provide. We can't meet it with corn. And so on down through here, and you'll see a couple others, methionine and tryptophan, valine. If we fed just corn, the pig's not going to grow well because that's going to limit protein synthesis. There won't be enough of those ingredients in the cell to make the protein he needs to make. Well, how do we fix that? Well, let's throw away corn. We know soybean meal is very high quality protein, very high concentration. Well, let's feed them just soybean meal. We go through the same exercise. Well, it looks pretty good from a nutritional standpoint. Every one of these bars, the soybean meal is providing way more of the amino acids than the pig's needs, so we'd have all our needs covered. Well, obviously that's not going to work because of expense. And then all this excess amino acid, the pig has to deal with that, and it's kind of a load on the system. So that's whenever we do the blending. And basically we make this corn-soybean meal blend. And we're targeting lysine. We make that blend in the proper ratio to make sure that we meet this lysine requirement. And if we do that with natural protein sources, all these other amino acids are going to be in excess, hopefully a little bit. And we can satisfy that need. And so it's basically the balance of these amino acids in the natural ingredients that dictates whether the ingredient is a good quality ingredient for pigs or not. And that's whenever we come in with some of the synthetic amino acids. If we add some synthetic, we can use less soybean meal and pull some of these excesses down, but still meet the pig's requirement. So that's the idea of amino acid balance, and why when I as a swine nutritionist look at a feed ingredient, a lot of the agronomists will tell me, well, it's high protein, and I don't really care. Tell me what the amino acid profile is. And in their defense, the agronomists are telling us that now too, so that's good. So in soybeans, we have some anti-nutritional factors we have to deal with. Trypsin inhibitors, tannins, alkaloids, saponins, isoflavones, kind of an estrogenic compound, glucosides, hemagglutinins, these kind of bind up protein digestion, phytate, ties up phosphorus, oligosaccharides. You look at this list, you think, geez, why would we even bother feeding pigs soybean meal with all those problems? And Seth, you can help me. These are kind of plant protection compounds, aren't they, or something like that? Why are they there? Some are, okay. But from the pig standpoint, they can create problems. So what I did is I picked out two, trypsin inhibitors and oligosaccharides, to just share a little bit of data with you on. We go to the oligosaccharides first. Basically, we're looking at Stachyose and Raffinose. These ones are, they cannot be cleaved in the intestine of the non-ruminant. Pigs don't have an enzyme called 1,6-galactosidase, so they can't break down this carbohydrate. Poultry, and I won't show you data today, but poultry are very sensitive to the Raffinose and Stachyose content of the diet. It causes wet droppings, wet litter, decreased digestion, so it's a pretty big issue in poultry. And because pigs are monogastrics the same as poultry, there's been some interest in this from the pig standpoint. So basically, we look at the structure of Raffinose and Stachyose. Basically, there's 6 carbon sugars units that are tied together. And it's this linkage right here, this 1,6 linkage in Raffinose, and there's 2 of them here in Stachyose, that the pig can't break that off. So he can't use these sugar units for energy. So they stay in the gut, they draw in water, potentially can cause loose stools and maybe some diarrhea. So Sam Baidu, my colleague at Waseca, did a project with AURI and some low oligosaccharide soybeans. He just finished it up here in the last 3 or 4 months, and he shared the data with me. Basically, they wanted to evaluate low oligosaccharide soybean meal as a potential for early wean pigs, with the idea that maybe you can help reduce some of the loose stools, some of the nutritional diarrhea that might occur with high levels of bean meal in these young pigs. So basically, they had soybean meal, just kind of a regular commodity soybean meal, and then a low oligosaccharide soybean meal, and look at the differences here in terms of dry matter. Crude protein was a little higher in the low oligosaccharide meal. Some differences in fiber, ash, the mineral content. If we go look at lysine, a little bit higher in the low oligosaccharide meal, I would assume, since it took out some of those sugars that concentrated some of the proteins. And down through here, in general, it has a little bit higher amino acid concentration than some of the important amino acids we're concerned with. If you look at the meal itself, the oligosaccharide content, genetically they were very effective at taking out Raffinose, and Stachyose were just very small levels, low levels remained in that low oligosaccharide meal. And basically he ran it through pigs. This is the research nursery unit at Waseca. Individual or small flat deck pens, small groups of pigs in there. They started at about 13 pounds, I think. And basically they ran 4 treatments. A corn soybean meal control, basically a corn diet where the soybean meal was half conventional meal and half the low oligosaccharide meal. Then a treatment with all low oligosaccharide meal, And then a fourth treatment, which is basically the same as 3, except they took out all the goodies, the whey, the fish meal, the spray-dried porcine plasma, and see what the performance would be with a pretty simple diet. Fed on in 3 phases, 1 week, 2-week phase 2, and then 1 week in phase 3, so a 28-day experiment. Look here at the diets real quickly. Basically corn base. In the 50-50 diet, it was half of the protein was provided by conventional meal, half the protein by low oligosaccharide. And remember, the low oligosaccharide meal was higher in protein, so they didn't have to put as much in the diet. And then this treatment over here was all low oligosaccharide. And all these treatments had fish meal, whey, and spray-dried plasma. And then the final treatment was just corn, beans, or bean meal, and then the vitamins, minerals. That's phase 1. Phase 2 was very similar, again, with whey and spray-dried plasma, fish meal in it, and then this kind of simple diet in treatment 4. So if we look at some of the growth performance, as I said, they started, I apologize for the kilograms, I missed that when we were putting this together, but basically they came on study at about 12 pounds. After 28 days, they weighed pretty much similar across the treatments. We would have expected if there was a big benefit of the low oligosaccharide meal, these pigs maybe would be heavier at the end of the trial, and they statistically were not different from the controls. If we look at average daily feed intake, I'll point out that this is an expanded scale. It doesn't start at 0, so these differences look a lot bigger than they are. Basically, statistically, there was no difference across the 4 treatments. So the feed intake for the controls was not different than the 50-50 diet or the all oligosaccharide diet. Feed efficiency, gain to feed, was not different. And so basically we would have expected that if there was a problem with Stachyose and Raffinose, that these pigs should have been performing better throughout the study, and they did not. This is an agreement with some data that I had a master's student several years ago take conventional soybean meal, and she used ethanol to wash the soybean meal and extract the oligosaccharides out. So she took out the Raffinose and Stachyose and took out sucrose as well with ethanol wash. And so that was her second treatment. So basically the diets had essentially no Stachyose, Raffinose, or sucrose. And then she took that wash water and dried it, and so had the residue that was left in there, which would be the combination of these carbohydrates. She added that dried residue back to this diet, so tried to mimic the control diet. And then her fourth treatment was, she said, well, let's just take pure Raffinose and pure sucrose and put enough in that would be similar to this control diet. So we try to isolate what the pig's response is to Stachyose and Raffinose. And basically what we found is it didn't matter. If we look at the blue bars, the light blue bars is average daily gain, average daily feed, or gain to feed, and across any of these treatments, statistically, there were no differences in performance. So basically, these 2 studies tell me that the pig, particularly the young pig, and we would assume it would be similar for the older pig, really isn't that sensitive to these oligosaccharides, the Raffinose and Stachyose. Switch gears to trypsin inhibitors real quickly. Trypsin inhibitors, 2 types, the Kunitz and the Baumann-Burke. Kunitz are about half the trypsin inhibitors present in soybeans. They interfere with protein digestion. Trypsin is an enzyme in your stomach, and it's one of the early enzymes to break down proteins. A trypsin inhibitor doesn't allow that trypsin, that enzyme, to work. Fortunately, if we heat the soybeans or the soybean meal, we can destroy those trypsin inhibitors, make them inactive. And we know that young pigs are more sensitive than older pigs to these inhibitors. Well, what would be the advantage of the low trypsin inhibitor beans that Seth was talking about? Well, theoretically, you could feed these beans to pigs without heat processing, so they're saving some costs and some time. Or maybe we could just use a reduced amount of heating and still get good pig performance, so lessen the burden of processing. Here's some older data, basically looking at nursery pigs in the light bars and grow-finished pigs in the dark bars, and comparing conventional soybean meal with low trypsin inhibitor beans and high trypsin inhibitor beans. And basically this would be heated, toasted beans, so that's our meal, that's our standard. And we see, if we look at the young pig, we see a pretty big drop as we go from conventional meal to high trypsin beans. And if we breed out the trypsin inhibitors, we get some improvement in performance relative to all of them being in there, but it still doesn't get us back to control. And basically, as my understanding is, these lines were taken out the Cunix inhibitor, but not the Baumann-Burke, so there's still some inhibitors left. If we look at grow-finished pigs, we see the similar response, a similar pattern, but the magnitude of drop is not near as large, so it suggests that the older pigs can handle this a little better than the young pigs. If we look at the effects of inhibitors on efficiency in pigs, same pattern. We see a big hit in the nursery pigs and not as big a penalty in the older grow-finished pigs. Well, what happens if we use these low beans and try to vary the amount of processing? Here's a study out of Kansas State, basically looking at the degree of roasting. And they looked at it in high trypsin inhibitor beans, so basically normal beans, and beans that were bred to have low content of trypsin inhibitor, and compared no roasting to half roasting to what would be considered a fully roasted bean. And we see that if each time we increase the amount of heating in the high trypsin beans, we get an improvement or a decline in the trypsin inhibitors. We look at the low trypsin beans, we still have some trypsin inhibitors there, and the heating reduces the amount of trypsin inhibitors that are there, but just at a lower level. If we look at pig performance on these, basically the high trypsin beans, the more we process them, we get better performance in terms of average daily gain. The low trypsin inhibitor beans start at a higher level, but they still don't get to the full performance advantages that we see with fully roasted beans. So basically, there's probably not a lot of advantage in reducing the heating because the amount you're saving in fuel here to process the beans would not offset the penalty in pig performance. So even with the low trypsin beans, there's probably a need to do some heat processing of those, particularly for young pigs. And here we look at gain to feed, basically the same kind of response. The penalty is not as great in the low trypsin beans as in the high, but there is some value in roasting those. So if we're going to roast these beans or heat them, the general guidelines are for dry heat roasting 3 to 5 minutes with a temperature of 240 to 260. If we're going to extrude them, an exit temperature of 280 degrees Fahrenheit, basically with a target, the end product to contain less than 4 milligrams total trypsin inhibitor per gram of product is kind of a standard you try to achieve in properly processing these beans. So the conclusions here, basically, from my read of the data, there might be some work in breeding low oligosaccharide beans. It's probably not going to be a big benefit to the pig producer. Pigs don't seem to be as sensitive to those oligosaccharides as we see in poultry. Young pigs, and I didn't mention, but lactating sows as well, are more sensitive to trypsin inhibitors than finishing pigs and gestating sows. So if you want to cheat on processing raw beans, the place to use those beans are in gestation and maybe late finishing. And still, even though we take the trypsin inhibitors out to some degree with breeding, there's still some benefit from heat treating those.